Okay, I think we're ready to start. Until we get a few more participants joining, just wanted to say hello. Welcome to this first webinar of IDIADA. We will be going through connecting automated vehicles today. Just a few rules about Zoom for who is not familiar with this software. You would be able throughout the presentation to send messages to panelists in the form of Q&A forms. So you have a button next to on the bottom of your screen. For the purpose of this webinar, all participants are muted until the end of the presentations. If you raise your hand towards the end and you would like to speak, ask us questions, we would be more than happy to accommodate that as well. So you have a button for raising hand. I repeat, this will be at the end of the session. So I believe most of the participants have joined. We are going to make a start. Ladies and gentlemen, thank you very much for joining us. First of all, we will be switching off the slides and we will be running through introductions of today's presenters. So Charlie, if you want to start.
Sure. Hello, everyone. I'm Charlie Warnaby. So I work for IDIADA in Cambridge in the UK. I was the project leader on the Maka project, which was a really exciting automated vehicle project where connectivity was key. So I'll tell you all about that in due course.
Hi, I'm David Evans. I'm leading the connected vehicle and V2X activities in the UK, and I'm also responsible for the IDAPT product manager.
Oh, can I just say to participants, do turn on your video panel as an option if you haven't already, so that you can see us. So we're waving and smiling at you, but by default, we're probably hidden. So if you go to the top where it says view options and do, I think, view video panel. Thanks.
Good morning, my name is Xavier Sellart. I joined IDIADA 10 years ago, where I have developed my career by developing ADAS and automated driving systems. So I'm the technical leader of CAV project, which I will explain during this presentation.
Thank you all. As a summary for today's discussions, we will be running through an introduction of IDIADA connected autonomous vehicles. We will be discussing about our IDAPT, which is a rapid development tool developed by IDIADA in-house. It's an onboard unit that Dave will explain in more detail. And we will be giving you practical examples of connected and autonomous vehicles, R&D projects, as well as projects for customers. We will quickly run through IDIADA introduction. I'm not gonna bore you with too many slides. We actually have a video for that. So if you want to go to next slide. So I hope that gave you a flavor of IDIADA's capabilities. In terms of locations throughout the world, IDIADA is based in, well, pretty much all continents apart from Australia. We are representing here the main centers for engineering, testing, and homologation in the form of our headquarters in Spain, our Czech Republic, our China branch, as well as Germany, Brazil, India, US, and also UK. We also have branch offices where we have key account managers like myself based and or homologation representatives supporting us with local regulations to be able to best support our customers. In total, we are 2,750 worldwide, and we believe that we are offering comprehensive services to our customers in the form of full development from engineering, testing, as well as certification support. Next slide, please, Dave. As you've seen in the video just a minute ago, IDIADA has capabilities in all vehicle areas, and we have knowledge in main vehicle functionalities. Main vehicle functionalities in which electronics play a key role, and we have around 100 people worldwide supporting with that. So we are supporting our customers with vehicle dynamics, passive safety, and active safety, powertrain comfort, reliability, NVH, but not only. Next slide, please, Dave. Now, focusing on electronics, as I mentioned before, we have a team of more than 100 engineers based in our headquarters in Spain, Barcelona. A second team in terms of size is based in our UK office in Cambridge, and three more project-based teams in India, Pune, and Germany and Czech Republic. In headquarters, my colleagues will explain further, but we have a variety of services that we are offering to our customers, not only in the ADAS field, but in traditional electronics as well. In the UK, we have more of a focus on connected vehicles, on functional safety, and SOTIF more recently. Next slide, please, Dave. So I'm going to hand you over to Dave now, who will introduce the IDAPT in more detail.
Hi, thank you very much, George. As I said earlier, my name is David. I'm heavily involved in our connected vehicle and V2X activities, and one of my additional roles is also the product coordinator for our IDAPT unit. So essentially, what is IDAPT? In probably summary, IDAPT can turn a non-connected car into a connected car for a number of different connected and automated vehicle R&D and proof of concept activities. It was a tool that we developed in-house in our electronics department, and we're using it on a number of different projects. We wanted a tool where we could develop proof of concepts, nice R&D activities, but we also tried to make something that could function independent to a vehicle's electronic architecture system, but also work just as well and possibly much more better when it's integrated with a vehicle's electronic architecture. So that might mean something like integration to several of the CAN bus within a vehicle, also integration to additional components, whether it's over something like digital or analog inputs, outputs, something Ethernet based, USB based, other forms of ways to get into a vehicle's electronic architecture. And we wanted something that was quite compact and small, such that it could be developed on a bench and then just as easily install it into a vehicle. So in the images below, you'll see what we started off with was a concept. The middle was our implementation, and the integration is an IDAPT in one of our research vehicles. The IDAPT you see here, we have a number or a selection of different connections into it. So they're both wired and wireless. You see in the top, you have a number of aerial inputs in addition to a traditional ECU connector in the bottom left, and also camera inputs. One of the nice things we have about IDAPT is that the majority of the components are quite modular based, in the sense that these modules can be removed. In the case of most components, they can be removed, modified, either and also swapped around. So, for example, if there was a preferred GPS unit or module you were quite fond of, we tried to design the PCB such that we could accommodate this. But inside the IDAPT itself, we've allocated a number of different components which we believe have been quite instrumental in a number of different connected and automated vehicle projects. So I can just take you through a selection of them now, which the Nvidia module is probably the heart of it all, let's say, in the center, which allows you to have a Linux environment. So if you have a number of different Python, C++, or ROS-based applications, it's quite a familiar Linux environment you can deploy your applications on. Just slightly below the Nvidia module in the center, there's an independent safety microcontroller. So these modules are, we wanted something that was independent to the Nvidia module, something that could act as a supervisor, or let's say be able to reset the application you're developing. Because quite often in the R&D space, you're trying many different things, many different versions of software, and you always want that independence to your application to make sure everything is running correctly. So to give an example, which my colleague Charlie will show later, if you have some application that's determining how a steering wheel is controlled, and you are not fully confident in your software, you may want that additional element that's keeping an eye on your application to make sure it's running correctly. Also, we've had a built-in battery because most often not when you're in the R&D space, you're consistently turning on and off the vehicle because maybe you need to reset some component. This was actually a requirement for our GPS module because we did not want to consistently lose power and then try to regain a GPS fix. So we had a built-in battery that just, let's say, kept things alive for a short period of time, it's less than an hour. The battery can run at full capacity, but also have a power supply so that it's happy working at 12 volt or also 24 volt inside the vehicle. So you can feed into the vehicle's power supply as well to keep your unit running. V2X is a pretty popular technology at the moment now. We're using it in a number of different projects, but we felt it was quite instrumental to have a V2X module inside because we wanted the ability to have vehicles communicating with each other, particularly for our R&D activities, which we'll show you a little later. The cellular modem, so that's also getting GPS correction data, but probably importantly, it brings some form of independent internet connection into the vehicle. So there's a slot on the bottom of the IDAPT unit to put in a SIM card, and then if you're doing some form of internet application, perhaps you're logging data from several components and you want to send it back to your base wherever, having that internet connection is quite important. Also having camera inputs. So we have 6 GMSL based camera inputs on IDAPT. So this allows you to take in camera input to support your image based application. Also Ethernet and broad reach. So many different components may not be CAN based, for example, but you may require something like Ethernet or broad reach, which is quite developer friendly for bringing additional high-speed data inputs into your applications. So, for example, a LiDAR can be brought into through the Ethernet connection. And also automotive grade I/O. So this is your traditional digital inputs, outputs, pulse with modulation, just select additional inputs such as CAN and with a modification FlexRay. And ultimately why we made IDAPT, we want to, let's say, taking the image on the left, which is probably a traditional vehicle with a number of different self-driving connected vehicle components, we've tried to condense that as much as possible. So quite often is the case, you have a different selection of cables, power supplies, different modules, different licenses, different versions of software. And we tried to reduce that down as much as possible by integrating components at an ASIC level into the IDAPT unit. But more importantly, we have software control over all those components. And as you can see, probably how we tried to highlight IDAPT is something like reducing all these components down to something much more smaller into the vehicle. And we're using IDAPT in a number of different ways. So for example, your automotive IoT proof of concept. So you may require to collect some data specifically from a number of different sensors, aggregate that data and also push it somewhere, whether it's to some backend server or some internet-based location. For path planning, so if you have a clever idea and you want to try out some form of path planning algorithm, then that's something you can possibly try out using the IDAPT unit. With vehicle data logging, so we're using this on a number of projects for collecting specific data from a vehicle and also pushing that somewhere. Safety monitoring R&D, so as I mentioned earlier, we wanted to be able to have some form of independence or supervisory monitoring of a application, which we'll show you later on the Maka project. Cybersecurity R&D. So we're working on a number of projects which involve, let's say, some form of cybersecurity, whether it's application-based or V2X-based. Because we have this flexibility in our unit, it makes it a lot easier to carry out those types of activities. Vision and sensor R&D. So we have camera inputs and high-speed data inputs such as Ethernet. So we are able to carry out some R&D for vision and sensor. And vehicle actuation, which we'll show a little later, is how we're using IDAPT to perform some form of vehicle actuation on a vehicle. And also V2X R&D. So on a number of projects, we're using both the SE ITS G5 communication standards for V2X, but in other projects, we're also intentionally not doing that. So while the standards are still ongoing in development, we wanted to try out our own ideas, and having this flexibility to choose whether you use the standard or not use the standard has been quite instrumental. And also just having IDAPT's a Linux-based system, so you have a wide variety of different open source technologies available, but we're also integrating it with a number of industry standard tools, such as Prescan, Carolyn Scanner. And I can take you through some of the IDAPT use cases now. So automotive IoT, so this is the project I'm involved in. And in this project, we're collecting data from a number of different components of the vehicle. So this is using a, let's say, a commercially available vehicle, and we're tapping into the different CAN networks to get at the data, such as steering wheel, speed, fuel gauge, throttle position. We're collating all that data inside IDAPT, and we're also intentionally introducing some attacks on a number of different areas of the vehicles. So whether it's an attack on the CAN bus, intentionally manipulating the data inside IDAPT, but also pushing that to the cloud-based server, which in this case is Fireware. But the interesting part about this is that we're also getting statistics on the vehicle's performance. So if you see on the right-hand side of the screen, we're collecting there's very small applications known as beats, which are monitoring specific parts of the vehicle, whether it's looking at the CAN bus, looking at the V2X incoming and outgoing messages, but also things like CPU and RAM statistics, and also pushing that to a component called Elasticsearch, which if you have any data scientists in your team, I'm sure they will be quite familiar with that. So this has been a project where we've deployed IDAPTs into some vehicles. We're collecting this data and intentionally injecting erroneous messages into it for assessment in the cloud. But there's a number of ways to, let's say, scale this up. So if you had another component in your vehicle's architecture that you were quite interested in monitoring, a tool like this could be used to assess a number of different data points for this, and also push it to your cloud-based solution for assessment. And I'll also just continue on with the vehicle data logging. So this was a project we carried out for a client. They had a need to deploy a number of vehicles to for testing activities. And we came in to integrate our unit with their architecture, and also develop some software to aggregate the data from a number of different components, assemble the data, and push it to the client's backend server. So one of the interesting things about this was that we did not originally have Wake on CAN or Wake on RTC, which is real-time clock. So the client asked us if we could incorporate this into our unit, and because we developed the hardware in-house, of course we could do that for the client. So one of the additional parts is that they wanted some form of smart health device, so a smartwatch, for example, monitoring the health statistics of the driver who was performing the test. So we were able to integrate the smart health device into the unit, which also collated all the data and sent it back. In addition, the client wanted us to be able to press a button on the steering wheel to start an audio recording. So the driver may notice something strange happening with the vehicle, and they may want to report on it. So once the driver pressed the steering wheel button, an audio recording would start with the microphone embedded in the vehicle, record the audio, put a timestamp on it, put a timestamp around all the relevant data, and push that back to the client's base. So that was quite an interesting project, in the sense that in addition to carrying out the testing activity, we were able to come in with additional engineering services and a solution for the client to, say, get a wider range of data collected for their own activity. I think that sums it up. So I will pass over now to my colleague, Javi.
Thanks, David, for the introduction. So in 2018, I was part of the team who developed IDAPT as a tool for the rapid prototyping of autonomous driving systems, with the main goal of having a flexible tool. However, at that time, we were not having an application. We were showing the capabilities, the real capabilities of the tool. So in 2019, IDIADA management decided to develop a robotaxi service at IDIADA facilities, but with a constraint of developing in 1 year. This was a challenge for me and also for the team, but we were convinced by having this tool and also this framework to develop it in time. So in the following video, you could see the concept car that we developed. David, can you?
IDIADA has aligned its development and validation expertise to engineer a Level 4 autonomous car, meeting the functional requirements necessary for safe operation within its headquarters. Using an HEV production car as a base, we have developed, designed and integrated an array of connected and automated vehicle subsystems and supporting devices. The vehicle is equipped with a computer platform for autonomous and driver assistance, the IDAPT, a multi-purpose electronic control unit developed by IDIADA, as well as multiple perimeter surveillance sensors. The development, integration and validation tasks undertaken by the different teams of CAV experts enable the CAV ride to predict and understand the road environment for safe, driverless navigation within IDIADA's headquarters premises.
Okay, so basically CAV Ride is a robotaxi of level 4 of autonomy and is offering a service in our facilities for allowing our clients request to pick them up. Then they can select the stop where the vehicle shall go autonomously. As you can see, the operational design domain or ODD of our vehicle at the moment is very small, but we have been able to demonstrate with our toolchain how we can develop an autonomous car. In the following years, we will be increasing the ODD of the car in order to make it work not only at IDIADA facilities, but also outside, for example, in cities or something like that. David, next. The development of a CAV system is a challenge for the automotive industry, not only in software development, but also in the technology. Okay, so we are having new constraints in safety, in new technologies. Also, artificial intelligence is quite relevant. So in order to deal with this, we started the project by defining all the use cases of our robotaxi in the route where the vehicle should work. And also another part that was really important was to follow standards such as where we defined all the scenarios where the vehicle should work. Okay, so once we have this line of requirements and also of scenarios, we started the system development phase. And during the system development phase, we developed a domain architecture. Okay, so that domain architecture had as a brain or as a heart of the system IDAPT. Okay, IDAPT basically was working as a domain controller, and basically that system that we developed was divided in the following subsystems: the perception, localization and mapping, planning, vehicle control, and HMI. All of those were requiring some expertise, very concrete, but the good part of it is that with our toolchain, we were able to develop such algorithms in a very smooth and smooth manner. Next, David. Okay. Put the video, David. Okay, so basically our perception system processes data from sensors into a structured data that can be used for the next planning and control algorithms. This is where most of the vehicle analysis takes place. This subsystem is composed basically by software components such as lane detection, traffic sign recognition, objects detection, free space detection. So one of the important things to remark here is that we were using data from different sensors, and we were also developing data fusion algorithms. And also, another important part to remark is in the part of positioning, which is we were using also HD maps. Okay, basically at IDIADA, we are not only having physical facilities, we have also scanned all our test tracks, and we can use such digital maps in order to develop position algorithms. And those maps can be used not only during the development phases, but also for the verification phases in the real testing activities. Next, David. So once the sensor data is processed by the perception system, that can be used by the planning module that we have developed. Basically, this module we have divided in three main parts. One is the route planner, which basically is the module which is responsible for deciding how to go from the point A to B. Then we have the behavior module, which is basically deciding which maneuvers the vehicle should take. And later on is the trajectory planner, basically deciding the route, the trajectory that the vehicle needs to follow. Lastly, that trajectory is sent to a control algorithm, which is called MPC, or Model Predictive Controller, with the main goal of sending the commands to the actuators to follow the decided trajectory. In the video, you can see the framework that we developed for developing these kind of modules. So this is important. It's important to remark that what you can see in the video are the scanned digital maps from IDIADA. Basically, those are our engineering streets, and we are using standards like OpenDrive. Okay, this OpenDrive HD maps, we are using it for our algorithms in the vehicle itself, but also for our simulation environments. And also, what I would like to remark in this part is the flexibility of IDAPT, because one of our constraints was to use MATLAB Simulink, because part of the team was very kind to use this framework for the development activities. And with IDAPT, we were able also to implement and to integrate Simulink models in our project. Next, David. So one important part also of the project was the HMI concept. And also one of the important things to remark here is that the HMI is not anymore only what it is inside the vehicle, also is what is outside. Okay, basically, the vehicle was having an infotainment system where the driver and the passengers could interact, but also there were users, external users with mobile application where they can call to the vehicle itself. So basically, for developing that structure, we had three main modules. One was the infotainment system, which was inside in the car and was communicated with the autonomous driving system. But also there was a backend, a server, which was managing all the calls from inside the car, but also from outside the car. And later, lastly, we were having a mobile application. David, can you? Okay, so I think one of the important things to remark in this part is that the human-machine interaction is quite relevant in the development of an autonomous car. And the process that we follow for doing that was to work with a human factors team, because they are experts in defining the requirements for this kind of applications. And we started by defining the use cases where the vehicle should go. Okay, and then from this, they started to design and to define a HMI concept. Okay, so basically then we were having a team dedicated to the development of the infotainment system, backend system, and also for the mobile application. And we developed all those features always in iterations, okay? Because many things that they were defining were very difficult to implement, so we need a lot of refinements. And also it's important to remark that we were also in contact with our marketing team in order to have the look and feel for the project. And this is basically the steps that we follow for the HMI. So, well, this is the robotaxi prototype that we have developed at IDIADA. I invite all of you to take into consideration IDAPT and IDIADA team for developing your AV systems. Okay, so let me introduce to the next presenter, Charlie Waterby, who is our technical lead of the Maka project and also has a lot of experience in connectivity and automated driving systems.
Thank you, Chavi. Yes, so I'm Charlie Waterby. I work for IDIADA in Cambridge in the UK, and I'm a software chief engineer. Now, for those of you who joined a little later, can I just ask you to go to the top of your screen and do View Options and Show Video Panel. That's partly so you can see me waving my hands, because it's difficult to explain Maka without waving your hands a bit. But also, after this, David will then be able to show you some kit using his webcam. So if you don't have your video switched on, you won't be able to see it. And I'm afraid it's not the default to show it. Okay, David, if you take us into the first slide about Maka then. So we're going to start with a video, and I'm not going to tell you anything about Maka before this video because it introduces it anyway. So yeah, take it away, David. Do play it. Thanks. Today we're at the Bruntingthorpe Proving Ground to demonstrate the multi-car collision avoidance, that's the Maka project system. What you'll see today is the two vehicles approaching some dummy obstacles. For the sake of this trial, what we do is set up the situation using safety drivers, then they both hand over control to the computers. Maka has control. And then the computers are entirely responsible for cooperatively steering the cars round the obstacles, working together, using their vehicle-to-vehicle radio links until the scenario is complete. This is the first time that anyone has demonstrated full-size cars working cooperatively together. It's like a hive mind or a shoal of fish. Avoiding collision. Here we just have two connected research vehicles, but in future all vehicles on the road can be connected. And the implication of that is that they can work together for cooperative collision avoidance like this. About 1,500 people a year die on the UK roads, and our objective is to reduce that number through automated collision avoidance of a really advanced kind. The Maka project, it's funded by the UK government by the Centre for Connected and Automated Vehicles with a total budget of £4.5 million, and we've been running for 2.5 years now, so these tests are the very culmination of the project. The partners to the project were IDIADA, doing the overall lead and software integration, Connected Places Catapult, doing systems engineering and coordination, Cranfield University working on algorithms, Cosworth Electronics working on perception and data logging, Westfield Sports Cars on test management, and Secured by Design on cybersecurity. We see this project as a springboard into further connected and automated vehicle technology projects, putting the UK at the forefront of this kind of work, which we believe is going to be really big. Great, thank you, David. So I do go on to the next slide. So there wasn't a lot of technical detail there, but I guess quite a few of you in the audience are reasonably technical. So I'll tell you a little bit more about how it actually worked. So firstly, Maka was entirely an IDAPT project. So IDAPT was first developed with Maka in mind, but also with other projects in mind. So we built in that flexibility so that we'd be able to use it for other things. Now you saw the key thing in Maka is that the two cars there were talking to each other. They were cooperating in real time. So the vehicle-to-vehicle messaging was absolutely fundamental to this. So we used ETSI draft messages. They're not quite standard yet to achieve that. So the main thing is that we used a maneuver coordination message, and that allows the two cars to share trajectory plans, and like that, they actually achieve the cooperation. There's also a collective perception message, and they can use that to share knowledge of the world. So if one car can see another car in front of it using its camera, it can transmit knowledge of that to the other vehicles around it using the collective perception message, so that all of the cars end up with a kind of unified, extended worldview. So those were two really nice features, which are entirely down to the vehicle-to-vehicle messaging. The actual control algorithm, it was one big application written in C++ using IDAPT, which is a free numerical solver, doing the model predictive control. Now, IDAPT is running Ubuntu, so you can run whatever programs you like. Although we were using C++, as David has said, you can use ROS or Python or whatever you want. But we worked in C++. We were using a camera to detect other cars. So that's connected to IDAPT using its dedicated, or one of its 6 dedicated GMSL high-speed serial inputs. And that's how we got knowledge of other cars which we could share over the vehicle-to-vehicle radio link. And the actual perception part, so that's detecting where other cars are in the frame, was done using a neural network based on SSD, single shot detector. And that was implemented on the GPU in the Nvidia system on chip, using the Tensor RT tools from Nvidia. The original model was in CAV. So, okay, David, can you go to the next slide, please? So the previous slide was about the kind of software, I guess. So here I want to show you some of the hardware. So in the bottom left, you can see that the IDAPT there it's got the kind of purple box around it. It's actually in the space where the spare wheel would belong. So it's underneath the boot or the trunk. So in fact, the boot space is entirely free for luggage. In fact, we literally took our hotel luggage with us from the test track when we finished trials each day in Maka. So that's very neat. So as David was emphasizing, that replaces a whole load of different boxes that people often have in research vehicles, lashed together with cable ties and Ethernet. So we just had one unified box. So then at the front of the car, if you look at that middle picture, the first thing to notice is the driver is holding a handle, that's the dead man's handle, with a switch. And you saw in the video that when the driver presses that switch, that's how we grant control to the computer, to the Maka control system. And then you heard there was a warning coming out of the car speakers, a spoken warning saying, Maka has control. And that was done from IDAPT, which actually has analog audio outputs, which we could feed straight into the auxiliary socket of the car stereo system. You can also see in that middle picture, there's an emergency stop button, and you can just see the corner of the touch screen. So on the right, you can see a screenshot from the display that we show on the touch screen. So that gives like a 3-dimensional view of the world as seen by the computer, as seen by IDAPT. It's just an HDMI screen, so that's fed directly by the HDMI output from IDAPT, and the touchscreen feedback is via USB. So that's all pretty neatly integrated. Overall, this is a fairly tidy installation, so we can use these vehicles for future work as well. And also, if they're appropriately configured, they're road legal to drive on the roads, which is very convenient. Okay, next slide, please, David. Right, so again, David touched on this when he was introducing IDAPT, and this was really important for Maka, is that we needed some safety architecture. So you saw in the glossy video we started with that we've got these 2 vehicles driving right next to each other under fully automatic control, and there's an obvious hazard that if one of them decides to turn the steering wheel sharply, then there's a definite risk of collision with the other vehicle. We were actually using trained safety drivers, but even so, they wouldn't have enough time to react if one computer just said, give me full steering lock. And bear in mind, this is a research project, so it's only prototype software. It's not kind of validated to production standards, although that's something that IDIADA does on other projects. So we had to use the safety architecture built into IDAPT. So we had a separate process running, which was kind of policed by that independent safety micro. So the safety micro has some dedicated outputs which can be used to control things at a hardware level. So we were using them to control a relay which just cut the power to the robot system if there was anything wrong. And that would definitely ensure that the driver had full control of the steering wheel again. So that separate process was monitoring the steering wheel position and the road wheel speed as well, directly from the production vehicle systems, completely independently of the Maka control application. So if it ever saw a rapid movement starting of the steering wheel, then much faster than a human reaction, it would kill the power to the robot system, the driver would have control, they'd get a verbal warning, and it would kind of solve the safety problem. And that's what allowed us to have two cars side by side under fully automatic control. That really enabled that demo. And it needed that safety architecture we'd built into IDAPT to do it. Okay, next slide, please, David. So I'm going to show you one more video, and this is the last part of Maka I'll show you. And this is going to be about the test environment. So we had a hardware in the loop concept, which meant that we were using real IDAPT units, but they were all hooked up to a simulation tool, which in this case was pre-scan, but it doesn't have to be pre-scan. As Xavi mentioned, at HQ in Barcelona, we've also used Scanner and Carla, for example. And this is how we did the testing. And it also shows how the Maka concept could be extended to multiple vehicles. So, okay, do roll the video. Thanks, David.
This is a digital representation of the Bruntingthorpe Proving Ground in the pre-scan simulation tool. And each of those white cars is being controlled by a corresponding real IDAPT unit here in the room.
Pre-scan sends fake sensor data to each IDAPT, which responds with actuator commands which control the simulated cars. Meanwhile, real vehicle-to-vehicle radio messages are sent between IDAPTs directly.
So each of these IDAPT units integrates the computing and communications and positioning. Each IDAPT is connected to its own screen, showing its own view of the world. And each IDAPT is sharing its trajectory plans with all of the others via its real vehicle-to-vehicle radio. Here, the yellow is the ego car, that's this IDAPT, and the green ones are ones it hears about using the vehicle-to-vehicle radio from its peers. The purple is an obstacle to be avoided. On the test track, we've shown two real Maka vehicles. But here in the simulation environment, we've got 5 vehicles, which shows that the Maka algorithms are not specific to only 2 vehicles. The key thing here is connectivity. What's happening is that each IDAPT is communicating its trajectory plans with all of the others, and that's how, together, as a group, they come up with a solution to the scenario, dynamically planned in real time. It's not scripted, the computers are working it out for themselves.
Great, I think that's about it for Maka. So can I just encourage everyone to turn on your video panel if you haven't already. So go to the top, view options, show video panel, and then I will hand back over to David, who'll give you a quick summary.
Thank you, Charlie. So just to give a summary on our kind of next steps. So we were originally using a DSRC-based V2X module. We've since upgraded that to support both DSRC and PC5, so kind of a hybrid V2X. Hardware is already built in and the software is currently in progress. We're currently upgrading the Nvidia module. So since we set out to design IDAPT, the Nvidia modules have since moved on a bit and we are just keeping up with that. So we have initially integrated the latest Nvidia module and we are continuing that development. A roadside unit IDAPT is in progress to support our testing activities and V2X activities. So for example, this could be used for something like a smart traffic application. So having some form of RSU-based IDAPT to communicate V2X to other vehicles, but also have some form of internet backend into a traffic management system to extend these types of V2X smart city type applications. We're experimenting with things like embedded SDR, so software-defined radio, for a number of different cybersecurity activities. And continuing, we've started out initial integration with MATLAB and simulating tools, so we're continuing with that. And we are utilizing IDAPT in a number of different funded projects, whether they're UK-based or European-based. We're quite open to partners, should you need a partner such as IDIADA for any form of consortium or group of members. And conclusions. So as we've demonstrated, we're using a IDAPT on a wide variety of different connected and automated vehicle use cases. We've done some world first V2V demonstrations involving robot controlled vehicles. And we're also quite capable of supporting niche testing and niche development activities for clients in automotive IoT and testing activities. So we're ready for tomorrow's projects. We're hardware ready for CB2X. We've already allocated footprint or space for 5G modem, and we're integrating the next generation of Nvidia modules, RSUs, which I've touched on earlier, for smart infrastructure activities. And we're essentially ready to support you with your needs for CAV prototyping, CAV R&D. But most importantly, it's a flexible, portable, and modifiable tool supporting your development needs. And how can we fit IDAPT into your own applications? I think that's it from my side, but finally, I would like to take this opportunity to quickly show. So what we have here is the IDAPT unit itself. As I described earlier, there's a number of different connections on it. So your wireless interfaces, your broad R reach, your SD card, your SIM card, your HDMI output, Ethernet, USB, and your traditional automotive ECU connector. We have our antennas at the front here, and a nice big heatsink on the top to keep everything cool. And finally, I'd just like to try switch cameras at the moment. Wonderful. So what we have here is one of the IDAPTs from the demonstration you've seen earlier. And it might not be that clear from the camera, but we're just collecting a number of different, let's say, CAN messages from other sensors. So this is generated from a CAN tool. But one of the nice things about it is that it's quite flexible. So at the moment, we're doing some form of CAN-based application using 2 of the CAN networks or CAN channels available from IDAPT. But there may be times where you are, let's say, waiting for a colleague to remotely log into IDAPT to update software, for example. And this was one of my requirements, that when you're waiting for your colleague to update his code via something like SSH or Telnet, then maybe you want to play something like Doom on your while you're just waiting for him to update. And that is it from my side. And hopefully we can just jump back to Q&A.
Okay, thank you very much, David. We do have some questions from participants. I doubt we will be able to answer all of them in the 5 minutes left. One of the questions is, and I believe you've already answered it in the presentation, but one of the questions is, which Nvidia system on a chip is being used?
Yeah, I'm happy to answer that. So we are using we have been using the Nvidia Jetson TX2, and we are currently, we have done initial integration with the Nvidia Xavier module, and we are currently continuing with that development at the moment, especially for the RSU.
Excellent, thank you, Dave. A few common questions throughout the list. Their subject is, please could you share contact details? You have them on the slide here. If you contact IDIADA_UK@IDIADA.com, we would be able to answer your questions either from a commercial point of view or a technical point of view. So thank you very much for your interest. Next question is, what kind of features are implemented and usable by mobile application? I think you had an example about a smartwatch. Is that comparable, Dave?
I'm sorry, George, could you just repeat the question? I just broke up slightly.
Yep. What kind of features are implemented and usable by mobile application?
So in the case of the smart health device, we integrated, so we developed an application for the smart health device. which was collecting the data from that device. But because IDAPT had a Wi-Fi access point built in, we were able to bridge the device itself with the IDAPT application. So it was managing the data collection over Wi-Fi. We had a separate application, let's say, taking in that information, performing some form of aggregation or collating that data together into what the client needed, which was, let's say, a periodic data collection from the smart health device, and then that would go into the input or be recorded for the clients, which would essentially be a few files that then just got pushed to the client's backend server. So we were supporting the let's say the integration of the smart health device into IDAPT, encapsulating or collecting that data into a preferable format, and then pushing that data then for the client, in addition to the additional information we were collecting.
Okay, thank you, Dave. One on Maka, Charlie.
Okay.
Can the principles of Maka be implemented onto any vehicle on the road, any other manufacturers?
In principle, yes. Now, Maka would be, it wouldn't be economically viable to kind of retrofit just as a safety system, because it needs the perception, the control, the automatic actuation. So it really only makes economic sense if you have a vehicle that's already intended for some kind of automated driving. So it already has the actuators, it already has the sensors, and then it just becomes a software feature. Of course, you do also need the vehicle-to-vehicle radio. And an aspect of Maka that we didn't mention during the presentation is that it also included a model which predicted where other vehicles on the road go that are nothing to do with Maka. So that means that even if you were the only Maka car on the road, if there was a sort of near accident situation, the idea is that it would do its best to figure out where all the surrounding vehicles were likely to go and do its best to avoid where they're likely to end up. So that means it becomes an immediate, useful safety feature even before there's any kind of mass adoption. So yeah, I suppose the idea could be translated to other vehicles, but it would only be worthwhile if they were going to have sensors and actuators and some kind of automated driving already.
Okay, thank you very much. And Xavi, one for you. As part of HMI, what are the possibilities that can be explored by IDAPT? Can you please explain on this? And also, what is full form of connected and autonomous vehicle?
Yeah, of course. Thank you for the question. So basically, in the current project, we developed the HMI application using Qt in an embedded PC. Okay, so we changed the whole HMI concept. IDA was working as a unit which was communicating with the server and then sending the data to the car PC where was implemented the HMI application. Okay, however, now we are working in integrating an hypervisor in the IDAPT, which will allow IDAPT to have different virtual machines where we have a specific operating system dedicated to such new features. Okay, so one of the things that we are investigating is having an hypervisor and having different applications. Okay, because the first goal of IDAPT was to be used as a rapid prototyping tool for automated driving, and that's why at the moment is prepared for that. So we see this need of infotainment system, and we see that every time the systems are more centralized. So we believe that we need an hypervisor and then to have virtual machines which will allow us to have a much safety capabilities in our system by isolating the applications, and also will allow us to have new features such as infotainment systems in the IDAPT. Okay.
Oh, just to chip in there, on Maka, we also used Qt or Qt for our HMI, and that was driven directly by IDAPT. That was just part of our C++ program. So, it can work either way.
Yeah, and regarding the CAV system, basically, as I have explained before, we have the system is basically following a domain architecture, IDAPT working as a domain controller, but it's important also to remark that we are using a Drive PX2, which is managing all the data from the sensors, because we are using artificial intelligence algorithms, which needs a lot of power, a lot of GPU. So that's why now we are improving IDAPT by using the new processor from Nvidia and adding the new Xavier, which will have more performance in GPU terms. Also, we are having the car PC that I have explained before, just for managing the infotainment part. Also, the IDAPT is communicating with the server, which then we are having a mobile application from where you can communicate with the car itself. And a part of this, we are also the part of let's say the part of the vehicle actuators is an interface that we have with a kit, and we are just sending commands, actuation commands from our IDAPT to that system. Also, another thing that we are having in the system is the possibility of integrating ADAS functions in one part of the IDAPT, because IDAPT is composed by a SOC from Nvidia, but also is having a microcontroller, and we can also integrate some of the features in the microcontroller, features such as AV, which are working as a safety features. Okay.
Excellent.
Thank you.
Thank you very much, Xavi. Thank you for this comprehensive answer. Would like to thank you all participants. Thank you for this webinar. Thank you all for attending. Wish you all have a good day, and we will see you at the next one.
Okay, thanks everyone.
Thank
Thanks
you,
for coming
everyone.
along.